There we go. Hello. I feel like I'm like 20 FPS. Hello everyone who is watching. It's been a while, but yes, hello indeed. I'm SolarLune. I'm an independent game developer and programmer and musician and stuff. Welcome. Welcome to the stream. I'm the creator of Tetra3D as well, and that's what we'll be looking into today. Tetra3D, which is a Golang 3D renderer. It's basically rendering everything from scratch, more or less. So that's what we'll be working on. But hello to everyone who's watching and everyone in the future as well. Hope everything's going well for everybody. I'm streaming a little bit earlier today because I won't be able to stream from my normal slot, of 5 to 7-ish PST. So this time I'm going to go from 4 to 6 basically. So yeah, that's the plan. Let me get some music going and we'll see how everything goes. Let's see, let's push this down to like -32-ish. Let's go with this. It's calm. It's calming. All right, so Tetra3D is a 3D renderer, as I mentioned, that I've written or am writing in Go. It works pretty well. It's basically on the level of like a PS1 renderer, that kind of thing. Everything's going pretty good with it. But I've been working on trying to optimize it, and yeah, that's where I currently am. I'm going to take a look to see what the current state of affairs is, because I haven't done any work on Tetra3D for a little while, for a couple of weeks. So let me head over to the logo, examples logo. So I want to see basically what it currently looks like, how it's running, what the issue is, or how everything's going. And the thing that I wanted to do this session, if possible, is maybe see about moving from float 64 to float 32 for all of the data, the mesh data and things like that, because the idea is, even if, well, initially I kind of had an idea, or earlier in Tetra3D's history, I had the idea that maybe float 32 calculations would be faster than float 64 calculations, because you're calculating a shorter number, and then when I saw that it wouldn't be, there wasn't really any difference, I was like, okay, well, maybe it's not that big of a deal. But then there was a post on Reddit that talked about in our game dev that said basically, why do people use float 64s, I think, for game development? And people were replying saying that developers use float 32s instead of float 64s, it was basically float instead of double, so float 32 instead of float 64 for Go. And people were replying that basically by using floats instead of doubles, you have the ability to store twice as many values, twice as many numbers in the cache, which is basically the storage space for memory near the CPU. You have a few levels of cache, and then RAM. RAM is the slowest out of the options of like L1, L2, L3 cache, and then you got RAM, and then you have your hard drive or SSD, right? So RAM is not slow; it's a fast option. But if you want fast, if you want to avoid taking time copying data into memory and out of memory, then you want to optimize your cache, right? Optimize your cache usage. So we'll see if I can migrate Tetra3D over from float 64 to float 32 and see if that makes a difference for what we're doing, because everything we're doing is basically on CPU except for drawing triangles and doing shader work. So it might be a significant improvement. We'll see. So let's see what this looks like so far. I don't remember what I was working on. I don't remember a lot. This can close as well. Okay, this is basically correct. Okay, this is pretty good. Let's head back over here to stress. See how this goes. So we're drawing 54,000 triangles at roughly 16 FPS. And it kind of wavers, sometimes going up, sometimes going down. I feel like this used to be faster. Wasn't this like 24 or something? So this might be like something introduced by my window manager or something like that, because I feel like this used to be higher. And I didn't make any changes as far as I know. Actually, it might be due to drawing the frame rate, drawing the debug text. A little bit of that. Yeah, it's a little higher. Snowmink says hi. Hello. Welcome to the stream. So yeah, 18, 16, 18 FPS. All right, all right. Let's see if we can compare this against Tetra3D as it used to be. I feel like I'm getting different results sometimes. Like sometimes I get, you know, a result that makes me feel like, hold on. A result that makes me feel like things are improving, and then sometimes I get a result where it's like, you know, it's clearly the same, basically. $15, $14, $14, so it's 15-ish. This is kind of centering around 15 FPS, more or less. Sometimes going lower, sometimes going a little bit higher, but it's basically 15-ish. There's a 16, but for the most part, it looks like it's about 15. Over here, it was basically 16, 17. There's some 18s in there. Yeah, so let's be a little bit more exact here. We're gonna copy this. This is the new version here. Let's see. Shows an easier way to do this. The average is 16.8 in the new version. The old version we're looking at 14.4. So 14.4 compared to 16.8. Okay, so that's 2 frames per second improvement. 14.4 to 16.8. That's 16.8 minus 14.4. That's 2.4. If we were to say 16. Well, I guess 2.4 divided by 16.8. That's basically a 14% improvement. That's pretty impressive. That's a good improvement. 15%. Not bad at all. Game Novice says, whoops. Game Novice says, let me close Discord. Yo, what did I miss? Nothing really. I'm just kind of getting back into the swing of things and examining the current state of Tetra3D, as that's what I'll be working on today. The thing that's a little bit different, or the thing that I'm going to try to do with Tetra3D here, if possible, is assuming that everything's in a good state with this branch, which is the branch that I was working on for indexed rendering. I'm going to try to commit that, and then maybe see if we can move the entire project, Tetra3D, over to using float 32s instead of float 64s, in the hope that we could store more data in cache and thereby make calculations faster. Because float 32 naturally takes half the space. A float 32 variable or value takes half the space of a float 64, and being that for the most part you're not going to be making a massive game in Tetra3D, you're not going to be making a big game or have a mesh that has vertices spread all, you know, across the universe. It makes more sense to just use float 32s, or even if possible some other smaller value. Maybe we can make our own, you know, vector that basically, or our own data type that basically just uses like int 8s or something, uint 8s, or int. We can do like int 32. Let's see, math max int 32. The maximum value of int 32 is 214-748-3647. So if we wanted to, we could do this, and we could say, let's split this up so that the last, let's say, 1,000 values are well, let me do it like this so we can copy this number. Yeah. So this is an idea. It's, you know, just an idea. So if this is the maximum value for an int 16 or int 32, then we could say, for example, 21474.8 or 8.3647. We could make basically our own float value that is essentially a float. Well, I guess we wouldn't need a float 30. We already have float 32s, so this wouldn't. We don't need to do this for int 32. But we could do a int 16. The maximum value of an int 16 is 32,767. So we could say your maximum values you can work with is 327.67. That's too small. There's no way. There's nothing you can do. You can, yeah, that's small. Game Novice says, for float, the binary coding is way different from an integer number. Yeah, the idea is, and Snowmink says, wouldn't using int give you jiggly polygons due to snapping values? Yes, but that's only at very small, like, precision, right? Like if our precision, let's say we were using an int 32 and for whatever reason, let's say we wanted to make an int 32 that acted like a float 32 with a fixed precision. So we say something like this: instead of having the maximum value of an int 32 be 214748367, we say we reserve the last 4 digits, or the first 3647 values, or really just the first 9999 values. We reserve that for the decimal point. Then the first, that basically means that we free up, or we have free 214,748 for the maximum like distance a vertex could be before overflowing, which most games, you're not going to have a unit that goes out that far, and you still have almost 10,000 points of precision, so you're not going to get snapping vertex issues really. You wouldn't really have that. It's just not, you wouldn't be able to see a vertex snapping between 0.0001 and 0.0002. You wouldn't be able to see it unless you were looking super close, unless it was super zoomed in. So I think and jiggly polygons due to snapping values or floating point precision errors can happen in modern 3D engines. Usually, you might see it, for example, if your game is really big, I suppose. If your game was massive, if you were making an open world game and you just tried to make it as naively as possible, where you just place something 100,000 units away, then when you go to that point and look at it with a camera, the vertices are going to be losing precision, and so it's going to be getting a little bit jiggly and wiggly and weird. So I mean, like, in truth, this, floating point precision errors or precision errors in general in visuals is a problem, and the solution, the workaround, is not to use float 64s, because that's just you can store half as many pieces of data in your cache, so that's not really a great solution. As far as I understand it, it seems like the better solution is to just like move the world every so often. So if your character moves 500 units forward, then once he hits the 500th unit, you just move the entire world back 500 units. So everything now is at position 00 instead of 500, etc., etc. And that's the general idea. Because that way you still have this seamless world, but it's, you don't have to deal with floating point precision errors. Or you could do it other ways, right? You could just move the entire world all the time, where the player never moves. It really is just offsetting the world by where the player would be. So if the player jumps, it moves the world down. If the player falls, it moves the world up, etc. So anyway, there's different ways to approach that, and that's really a situation where it's like you're looking for floating point error, or you have a game where you have floating point errors and you're running into this issue. But for a 3D renderer that's made for PS1 style graphics, you're not going to be making a massive open world game in this kind of engine. That's unlikely. So, rather than worrying about what 0.01% of people who might use this engine might want to do with it, including myself, it might make more sense. It seems like it would be more sensible to worry about what most people are going to worry about, which is usability, performance, things like that. Now, this still doesn't work because int32 is, as far as I understand it, as far as I know, it's an integer that takes up 32 bits of space, right? So that doesn't give us anything over a float 32, unless I'm mistaken. Let me see. A max float 32 can be higher. Whereas max int 32, yeah, is a lot smaller. I wonder, is a float 32 bit or is it 32 bytes? Let's see, an int 32 can be this big. Actually, let me do this real quick. Okay, let's see. Floating point 32 is a 32 bits in computer memory. Okay, so in 32, 4 bytes. That's 32 bits, 8, 16, 32. Yeah. So I wonder why int 32 is so much smaller than a float 32 in terms of maximum value. Oh, because it stores an exponent. Okay, so it stores an exponent or an exponent, and then you have a fraction and a sign. I see. So that's why it can be bigger, because it has the ability to store more numbers, whereas an int32 is just each bit represents basically each combination of bits represents one number. I see. I get the general idea. Okay. So then they're the same size. So then, yeah, there's no point in having a max using this concept with int32. We could just use float 32s, but we could do it with int 16s. But math.max int 16 leads us to there's 32,767. That's just too small. I could easily see you moving something out 300 units and then running into integer overflow values, and that's only with a fixed precision of 2 decimal points. So you can have a vertex that's 0.01 units away, and that's from origin or from another vertex, and that's a little tight. But it would be cool if we could do that. I feel like it would be dope. But yeah, I feel like that's a little too restrictive. .1 units, nah, that's just way too. Yeah, you need to be able to move at the very least. Game Novice says signed int, aka int, uint, unsigned int as in only positive numbers and 0. Yeah, we don't want to use just unsigned integers, because you could have vertices in both positive and negative space on each axis, and you could move an object in both directions on each axis. So we want to use not unsigned integers. We want to use signed integers or signed numbers. So our options would be like an int 16 or a float 32, because there's no point in doing an int 32 when you have a float 32. So that's probably what we're gonna do, is just do the float 32, because I can't imagine a world where I do this system and then on top of that make it so that you can easily add values to it or from it. Well, I can't imagine. It would just be a little bit more work to take an int 16, int 32 rather. Well, no, int 16, make it fixed precision floating point essentially, or have it pretend to be a fixed precision floating point number. Have you interact with it as a developer, and it give you a float 32. It basically casts the result of the division of the floating point and stuff to become a float 32, gives it to you, you assign it back, and then it turns silently into a int 16 again. That feels overly complicated. So I think float 32 is basically what we're going to be dealing with. It'd be great if we had a float 16. I feel like that would be dope. Let me see, is there such a thing? Golang float 32, float 16. I know it's not in the language proper, but maybe there is elsewhere. Float 16 package provides IEEE 754 half precision floating point binary 16 with a default for rounding. Closest conversion. Route to nearest. Conversions using pure Go take about 2.65 nanoseconds per operation. How does this dude do this, I wonder? This is an interesting concept. What is the float 16? It's represented using a uint16. I see. So he basically is doing bit stuff. He's messing around with bits to like make. I'm guessing he does it just like a float 32. The first bit is the exponent. Yeah, exponent shift bias. Okay, so he's doing the same concept, I think, but doing it in Go. That's an interesting idea, and I love it. But the problem is that when we go to do math, we'll have to convert from a float 16 value to a float 32 before we actually do the math. Because we can't do the math directly on the numbers because the numbers are bit numbers. Like, we can't just add a float 16 to a float 16 if we're doing addition, because the first bit in a float 16, or at least a bit in a float 16 might represent the exponent, so you couldn't just add them together. So this is dope and I like it, but we wouldn't be able to use it because I think it would take too much time to convert from float 16s to float 32s to do the math and then reassign them back. It said it took 2.65 nanoseconds per op. That's too slow. Like, it needs to be essentially free. So we'll work with a float 32, I think, if we end up doing this. Yeah, interesting idea. Love it. Absolutely love it. Absolutely love it. But yeah, can't do it. Game Novice says, wait, why are we going for float 16 in the first place? Well, the idea is basically by using smaller float values. Well, currently, Tetra3D uses float 64s for its mesh data, for its position data for nodes, like a game object, a model, or something like that. So all of these numbers are float 64s, which means that they take up so much space in the cache. So when we do vertex transformation, where we take a camera MVP, a camera model view projection matrix, and transform a model's vertices by this matrix, it can't store. It stores however many vertex information, however much vertex information in the CPU cache. These are float 64 values. If we use a float 32 or float 16, then we can store 2 or 4 times as many values in the CPU cache, thereby speeding up the process of vertex transformation. That's the general idea. So we won't be able to use float 16s because I think it'll be too slow to convert between float 16s and the float 32 number to do the math, because we can't do the math on the number directly because it's a uint 32 or uint 16, whatever. So we can't do that. So if we do this concept that I have, which should work, we would basically be looking at a float 32 instead. All right, so lots of talk, lots of talking. Also, sorry that I started a little late today, just by a couple minutes. I was out for a couple hours and I needed to grab something to eat just to resolve my body. Okay, so yeah, things are looking pretty good, running pretty well. Fantastic. Let's actually do a quick test. I'm going to profile this because I want to see how much of our time is spent doing vertex transformation in this example. Actually, let me turn that off and then do it again, because I don't want the debugging text to throw off the profile. All right, so that's done. Let's see. I don't know if I have this. No, I don't have it. Okay. I think it's like, oh, this is not correct. Yeah. HTTP. Is it like that? There we go. Cool. Okay. All right, so let's see here. Let's go to the flame graph. So when we're rendering the game, or when we're drawing the game, we're rendering the nodes, yeah. So in the process of rendering the nodes, some of the time is spent drawing triangles and doing depth testing and stuff like that, but a large percentage, which is 58 out of 86%, so that's a pretty large percentage. It's 5/8, almost 6/8. 58 out of 86. Well, almost 6/9. Almost 6/9. So almost 2/3 of the time we spend is spent transforming vertex, clipping vertex indices, which deals with float 64s, and also transforming the vertices in the process vertices function. Game Novice says, how do we read the flame graph? A flame graph, as far as I understand it, is basically at least as far as I understand how it's presented using Golang's pprof tool. It goes from top down, where basically each chunk, each square represents a function. So at the root, you have this big square, right? This big, the start. And then in there we have the run function. This is basically where we have our Ebitin game loop, or Ebitingen now game loop. And so it's updating frames, it's drawing the game, right? So these are internal functions to Ebitin. And you can see here it says ebitin.game. Let me see if I can zoom in. There we go. So you can see here it says ebitin.game for UI draw, image dumper draw, and then we have game.draw. So that's my game function, the draw function for this stress test example, which is here. So draw, this is where this function gets pulled in here. And then in here, we have render nodes. So that's where this is happening. Camera, g.camera.render nodes. And so in here, and so you can see it's calling Tetra3D.render nodes. So now it's calling the render nodes function on the camera in the Tetra3D package, which is what we're working on. And so you can see basically how the function is broken down, what's taking up time. The more red the function is, I think the more like time that function is spending. Maybe, but I'm not sure, because not every function is read equally. You can see it, there's definitely some color changes. I'm not sure what determines whether the color changes or not. I would think it's generally like, the hotter functions or the functions that take longer are redder, but it also could be that's, while that is how it works normally, that's not how it works for games, because games have idle time, right, where you're either taking input from events, event time, where it's taking input from events, or idle time, where it's waiting, right? Because if you have 60 frames per second and your game's not running on, if your game is pausing to maintain 60 FPS instead of running at full bore all the time, then that idle time can throw off the instrumentation. So anyway, the general way you read this flame graph, as far as I understand it, is it goes from top down, and it tells you basically the functions that are taking time. So in this case, processing the vertices of a model, that's taking up a pretty good amount of time. Rendering vertices is taking up a pretty good amount of time, and then we clip the vertices to the screen, which is really just transforming them to the screen, not clipping them, but that's taking up some time. So all this stuff that's taking time, I believe has, most of the stuff is dealing with float 64 transformations, like mathematics. So this is a good indication that the things that we talked about doing, the things I talked about doing, would have an effect. Like if it was where most of the time was spent drawing triangles, then that would basically mean that this wouldn't do much changing things from float 64 to float 32, because that's this would be the majority of time spent rendering a frame would be drawing the triangles, and that's something I have no control over. That's in Ebitin, right? Ebitension. But being that most of the time is spent elsewhere, that implies that this is in our control, so we might be able to do something to speed this up. All right. So yeah, lots of work on getting this to work. I think this is working okay. I'm not sure. Let me see. Oh, whoops. Not sure how this is gonna work. Seems like things are working largely okay. Look at this boy. Look at this boy. Okay. Let's see. I think that actually worked. I'm pretty sure I confirmed that. Cube lighting. Oh. Case sensitive. Exact match. By name allows you to filter a given selection of nodes by name. If wildcard, it's no longer called wildcard. If exact map, it's true that your nodes are going to be contained, otherwise they have to match exactly. Okay. Elias Daler says, sup, finally caught your stream. Hello, welcome to the stream. Hope everything's going okay. Codes of all nodes underneath the root, including the root node itself. Okay. Okay. This is a cube light. This makes me feel like I'm like working on Unreal or something, like an like an Unreal Engine from 1993. Lucretia says, "What's up, Solar? Hello, welcome to the stream. Thanks for stopping in." Alright, so this is working pretty well. Alright, well that seems to be working fine. What else? I'm just doing some text before I commit this because we're gonna make a massive change. And we want to make sure that everything is working okay before we do anything out of the ordinary. Lucretia says, nice, what's the massive change? Basically, well, I can actually keep this up as an example. But in Tetra3D, all of the mesh data and node data, everything, like, well, all the mesh data and all of the position relevant data, like position, well, transform, you know, your global transforms for your objects, everything uses float 64s. That means that we can fit however many pieces of data in the CPU cache using float 64s. What I had an idea to do, because of a thread on Reddit on our game dev, it might be better to use float 32s because then we could fit twice as many floats in the CPU cache. That might mean that it would be faster to compute mesh transformation and do basically to do math with Tetra3D. Things would render. It would be faster. It might be more performant to use float 32s instead of float 64s. And apparently I'm not wrong on that, because GPUs apparently are like tuned for float 32s firstly, and then secondly, I don't know if most engines even use float 64s. Like Unity, Unreal, and Godot might all use float 32s. I'm not sure about Unreal. Well, I'm not sure. I don't know, really offhand. But yeah, if a lot of engines use float 32-bit floats, maybe that's kind of indicative of a problem in my design that it doesn't. Or maybe it would be better if it used 32-bit floats as well for performance. So we'll see how that goes once we get in there. We'll see how much this improves, if at all. But I kind of feel like it might make a significant difference. Game Novice says, usually I've seen float 64 used in cases of high precision like timing. Yeah, I can see that for like if you're timing something, timing code usually needs that high precision. Yeah, maybe if you're doing something like Dance Dance Revolution or Osu, that kind of game where it's very, the difference between a frame or the difference between, click, like a perfect and a good is half a frame, then it's like, that you're getting into the area where maybe you need a float 64, or at very least you need to use float 32s and maybe just a little bit extra. A little bit extra, I don't know. Like there are situations with timing where maybe you don't want to rely on frames. It might be good like if you're working with Golang's like built-in timing system, like they're if you start a Go function, a Go routine, and you wait for like well, I don't know, I'm not sure if I can't imagine a situation where a float 32 would not be enough for timing in games. Maybe for like real life stuff, maybe like if you're doing something pretty hard, pretty rocket sciencey. But I feel like if you're making a game, a float 32 would get you so close to, like, I can't imagine you would need to be talking about a sliver of a millisecond, like a millionth of a millisecond. I'm not sure about that. But for real life things, there's definitely like situations where you would use a float 64, but for games, I think float 32 or even float 16 would be good. I kind of wish they had a float 16. I wish there was a native float 16 for Go. I feel like that would be kind of like perfect for my purposes here. Like it would be fast enough, or faster. Elias Daler says, are your vectors and matrices close to each other in memory now? I remember Vector did a lot of heap allocations, and ideally you'd want to put as much stuff on stack or in tightly packed arrays. I did try to move my vertex information to be as close to each other as possible. So before, all of like my mesh was composed of triangles, and each triangle had its own set of vertices and stuff, and you had a list of triangles, so it's like you like each vertex wasn't really close to each other. Now all vertices are super close because all of their individual attributes are together. So all of the positions are together, all of the normals are together, all of the lights are together. Really, I should probably put the position and normals in the same array or the same slice, because you usually read them together. Same thing. Well, UVs I think it might be okay, but basically, yeah, I'm trying to like push things together. So we'll see if that. I guess there's still room to improve on this. Now that I'm looking at it, it might be that I need to review how vertices are transformed and what properties are read and written, and put those things together. Yeah, I might be able to put like the transform position normals together, maybe. Vertex lights. Yeah, I'm still, it's kind of interesting because I kind of felt like there wasn't much I could do to improve this, the rendering process or the, Tetra3D in general. But like, I keep coming back to it and being like, oh, that would be a lot better. Oh, that would be a lot faster. Or let me try this. Let me, this would be cleaner, or whatever the case is. So it's kind of interesting. It's interesting to come up with new paradigms and new concepts that work for game development, or for something that you thought was like as good as it could possibly get, more or less. And it's like, nah, there's still a lot of room to improve. Okay, I think we're doing pretty good. Lachi says, howdy, hello, welcome to the stream. Thanks for stopping in. I feel like baking lights might be a little slow, but this is pretty good. Sitting at 2 milliseconds roughly. This looks really good. It looks a lot like PlayStation 1. Looks a little better than PlayStation 1 because, well, I don't know about it. Looks better than PlayStation 1. It looks like PlayStation 1. Looks better than PlayStation 1 implies it doesn't look like PlayStation 1. It does look like PlayStation 1, so never mind. Whoop. But yeah, this is pretty good. Okay. So everything seems to be working. Everything seems to be working pretty well. Elias Daler says, what I mean is that maybe a slice of vectors is not as good as a slice of an array of float 32s or 64s, because vector.vector is a slice, so you'll get a slice of slices, which may not be as close in memory. I did some testing, and I feel like it's basically the same, because when it allocates the memory for a slice, it allocates it in line. So it didn't really have a... Well, you might be right that a vector is bigger than a array of 4 floats or float 64s, because it has to store both the data and a pointer to the data. So that might be a little faster. That might be slightly faster. Game Novice says, if there's a way to view the disassembly, you could verify that suspicion. That's true. I could. Let's see. If I did do that, let me take a look here. If I did do that, then that would mean essentially I would need to make my own. I would probably make my own vector fork that essentially is just a 32 float 32 instead of float 64 vector. But this would mean that I would need to make 2 new vector structs, one of which being a 3D vector and one of which being a 4D vector, or I guess a 3-dimensional vector versus a 4-dimensional, or yeah, 3-dimensional versus 4-dimensional vector. I'm not sure if I want to do that. Thought about making vector matrix lib, but you can't do vec-tn. Yeah, I'm not sure. I have to think about it. I would have to basically like make an entire vector library like this. Essentially it would work like this, but it would have to be 3D and 4D. Maybe I could do it with like just a general getter and setter. So you could like anything that needs a 4D vector could take a 4D vector. Anything that needs a 3D vector could take a 3D vector. But then you could also just have vector be a type, an interface that basically just is fulfilled by 3D or 4D vectors. So if you don't care, like if you're trying to, let's say, rotate a vector, well, that only makes sense to do on a 3D vector, really. All right, I'm thinking. Let's start off by simply committing the things we have. Let's start with that. I'm just running through the different examples to see if there's anything out of the ordinary. Everything seems to run fine. Lachi said, oh, Tony D says, hey dude, hope you're doing well. I am, thank you. Lachi says, my experimental WebGL Go engine had multiple definitions for the variety of vector sizes. It was kind of a pain. Yeah, I don't want to have to do that. I mean, I think I should be able to basically just switch my matrix code to use float 32s and switch vector to be my own fork that is just a slice of float 32s, and essentially nothing changes. And I just keep the fork up with origin, with the remote remote master. But I mean, if it's gonna be faster, maybe I could just use a float 32 strictly for, I'm sorry, a 3D vector float 32 array strictly for Tetra3D's internals. So this becomes a 3D vector, and then the code that you touch is still the normal vector code, and it just kind of converts as necessary. That's an idea. Because then we could store even more data here rather than it being a slice. It's gonna be slower to access a slice, right, than to access an array. It has to be, because you have to dereference a pointer. It has to be slower. So that means that we would replace all of these with float 32 arrays, 4D or 3D vectors. Let's see. Vertex positions. Oh wait, I need model. That slice essentially contains a bunch of pointers to different places on the heap. The slice should be that, like that slice essentially. Yeah, that's true. Well, when it allocates the values, they should be. Oh, I think I see what you mean. What you guys mean. Well, but a slice. Oh. I think I see what you guys mean now. Even simple additions were 80 times slower and did heap allocations. Music Boy J Boy says, yo, hello. Hello indeed, welcome to the stream. That's, yeah, maybe you're right. Maybe I can, let's try this. Let's actually, I need to know about this. Well, I guess this is fine. We'll go to grids. Let's close all the others. Don't save. Okay. So what we'll do, I'll try doing a simple like test where we do this. T equals time now. This is going to be just very basic. Let's see. We'll just do 100,000 because it might crash otherwise. Okay. So we'll test this out. Okay, we'll test this out first. And then we'll do the same thing, but with arrays to see if it's a massive difference. Now, before I even start, I already know that this is going to be a little bit of a problem because it's going to take time to grow the slice. So we want to minimize that, or it should be equal, but it will be easier to just minimize that by doing this, by making the vector first. And we can set the capacity to be 100,000. And the same thing for the float 32. Yeah. All right, let's see how this goes. Jeez. No way. 6.5 milliseconds compared to 948 microseconds? Is that a microsecond? Millionth of a second. That'd be 1,000th of a millisecond. What's a picosecond? I always get those confused. It's 1 trillionth. Okay, so it's a microsecond. Oh my gosh. Okay. It's faster. Opinion, yeah, I'm not, I'm not testing the allocation. Well, allocation, yeah, okay. So this is, we already know that this is faster. It would be faster to allocate arrays, I suppose. I guess that makes sense. What we want to know is, would it be faster to do math? So let's test this like so. Okay, so we don't need to do this. We don't need to do that. Vectors. We say if I is less than 100,000. Vectors I equals vectors I plus 1. Let's see. 2. Okay, so something like this. 1, 3, 19, whatever. 7, 7, 7. Okay. So vector math. It's this, and then all right. So this will give us an idea of how much faster math can be. Yeah, it's a lot faster. Okay, so allocation of the data is a lot faster. Allocation of the arrays is a lot faster, sometimes of an order of magnitude. Or it's just like it goes from 6 milliseconds to like 0.6 milliseconds. Okay, so that means that basically the game might start up 10 times faster. Like whatever game might start up 10 times faster if we use arrays instead of vectors. And also for vector math versus array math, it's twice as fast at least. Sometimes 4 times as fast. Is that due to cache coherency? It might be. Let me see. I said it might be, even though I don't know what cache coherency is. Cache coherence is the uniformity of shared resource data that ends up stored in multiple local caches. Coherency. Excuse me. Have a cache copy of a particular memory block from a previous read. Suppose the client on the bottom updates and changes the memory. It does dynamic allocations even when you do A equals B plus C. I'm avoiding that specifically. I'm avoiding allocations because you can do in-place operations for vector allocations or vector math. Like if you go to model, here we go. The fast matrix multiplication vector like this, we just basically take the matrix values, take the vector values, and we do a matrix multiplication on the vectors, but we're not allocating data, not allocating a vector for this. And you can also do vector math in place. What's it called? It's not unsafe, where you vector.in. That's how you do it. So you can use vector.in to basically like do things in the slice without having to allocate a new vector for it. But I think it is going to be faster to do math and things because it doesn't have to dereference pointers. I think it's not dereferencing pointers. And it's just, it takes time when we're allocating a vector to allocate the memory. And then also to make a pointer to the memory. Both of those things probably take time. So this is a 100,000 vector slice. So that would be an object with 100,000 vertices. So it cuts it down considerably. 6 milliseconds to 800, 400 milliseconds to 200. Yeah, that's just better, dude. No matter how you look at it. I feel like the best way to test improvements would be to write benchmarks and then try to get speed and number of dynamic allocations as low as possible. I mean, yeah. I mean, yeah. Yeah, you're right. I just wanted to do a kind of a quick and dirty test, or I could see like, is this even a logical thing to try? Is this something that, you know, makes sense to put time into? It does. I mean, like we're clearly like we're getting the same result either way, right? So it's like it clearly must be faster because we're doing the same process on both. We're allocating the same amount of data, you know, for our uses. 3 float 64s. Well, actually, this is a float 30. This is a float 64. Let's try float 64 here instead. See how that changes things. It's still about the same. Oh, this took a long time this one time. 38 milliseconds instead of... I'll have to assume that's an outlier. Yeah, that might be like due to garbage collection or something. Array allocation 6579. Yeah, it's definitely faster. It's definitely faster enough where it's like I could try to make it work. And doing math on arrays is faster in general because we don't have to dereference pointers. Okay. All right, so here's what we're gonna do. I'll just comment this out for now. I won't comment. I'll just get rid of it. Here's what we'll do. If I wanted this to work, I would have to replace all vector usage in my code with a custom type that is essentially just a 3D or 4D vector. But I don't wanna write a vector library. I already did this for matrices, and it's just like I just don't want to have to do it, but that's okay. Tony D says, why not have an array of vector 3 structs? What do you mean? Why not have an array of vector 3 structs? Like a vector in... Oh, I think I see what you mean. You mean like for the mesh? Like an array of vector 3s instead of an array of expandable vectors. That's what we're talking about. That's the idea. So vector transforms would be 4-dimensional vectors, and then all the rest would be 3-dimensional vectors. But see, that kind of stinks to have like 4D and 3D vectors, because I can't share code between 3D and 4D vectors. But I mean, that's the point, right? Like isn't that kind of the point, is to make these things fast? And I guess vector code isn't really that complicated. Like there's not that much to it. You have add, subtract, multiply, divide, rotating vectors, normalizing vectors, getting the length, and that's kind of it. Like there's not much more that you'd want. Maybe reflecting vectors, and that's kind of it. Like you don't really need to. Well, I guess you'll need a clone. Scaling vectors might be nice. Inverting vectors. Yeah, so here's an idea. I guess this is what we're gonna do. What we're gonna do is we're gonna commit the stuff we have, and then slowly start working on replacing vector.vector with a new vector class or struct. Should I test this first? I guess I should test it first, but I don't even know how I would test it. Like what am I testing? Okay, let's do it. Let's test it first. Let's see, package. Oops. Let's see, benchmark. Okay, well. Elias Daler says, I remember I found some hot spot in Tetra where there was a ton of vector allocations and I replaced vector.vector with array there and it got some improvements. A good benchmark would be to do some skeleton animation calculations. Those usually require tons of math. Not sure if we can do that freely. Let me see. See, skin vertex is on model. It requires a clearer matrix. We'll look at vertex weights, which are float 32s. So it's a slice of float 32s. Man, I'll have to replace that with a slice of an array of float 32s if I really wanted to. I guess I don't have to. That's fine. Bone.transform. Oh, I guess it probably would be faster if I did, so maybe I should. Transform, void perk, matrix, skin matrix, matrix 4, skin matrix to add other matrix, scale it. This is probably bad as well. We shouldn't be cloning a matrix all the time. We should be doing it in... Yeah, why am I doing it like this? This shouldn't even be this way. Okay. Okay, this is definitely something we can improve on. What else? Okay, so we got the normal, we got the vertex out. Okay. Yeah, I don't think I can do this in code very easily. Or maybe we can just do some general calculations. So let's start off with allocating. And that's Okay, so let's test this out first. Arrays. So it says like the oops, three-dimensional array. Make. Oh, a slice. Oh, yeah, there we go. Okay. This might also help using an array of max items instead of a slice, which will grow and be on stack. That's true. Using an array of max items instead of a slice. Well, that would mean that we would have to allocate data on each model, or on each mesh rather, that is of a certain, an indeterminate maximum number. So, even if a mesh is one triangle big or two triangles big, like a quad, it would have, 90,000 or whatever arbitrary number, 90,000 vertex transform array spaces, 90,000 vertex positions. I don't know if that's a good idea, unless I'm misunderstanding. It won't work for model. I mean that for skeleton animations. You usually have an upper number of max bones. Oh, I see what you mean. Yeah. Oh. Well. I mean, but skeletons. Maybe you're right. Let me see. Bone influence scale by scalar. Weights. Right. So this is what you're talking about. So this maybe. Yeah, vertex weights should be like a maximum of 8. I think that's the GLTF. GLTF maximum is 8. So I could just make that a slice of 8. A slice of 8 floats. That would make it faster to access and write. And the difference between one float or one vertex weight and 8 weights isn't that big of a deal, because like it's a big deal, but you're not gonna have like a huge game full of hundreds and hundreds and hundreds of models or meshes that have bones on them. So it'll probably be fine. This could be, yeah. So replace. This could also vertex bones. That's how many bones affect an individual vertex. Is it 4 max? Maybe 4 max. I'm not sure. Vertex lights, that should be fine, I think. I'm gonna be done later. It might be better to see how vector.vector compares to a simple 4 float 32 or 64 array. Yeah, I think you're right. Okay, so let's try first just allocating this and seeing what the difference is. So go test. Go test equals bench. Is it? Let me see. I don't quite remember the. Go test dash bench. Oh, whoops. Okay, let's see. Benchmark load GLTF. Let's see. Did I misspell? Can there only be one bench Or, oh, it doesn't need to be, it needs to be probably named underscore test. There we go. Okay, yeah, that's how you approach that. Benchmark. Okay. Alright, so it's definitely 0, 1, 2. Allocating the vectors varies. Sometimes it takes more, sometimes it takes less time than allocating arrays. I wonder if it's because the random, getting a random number is kind of like making a wall. Let's try not getting any random numbers here because I don't want to have anything kind of interfere with the core concept. Yeah, okay. So purely just making the data and putting it in the array or in the slice is way faster if the data is an array as opposed to a slice. So we already know. All right. So we're benchmarking allocating the vectors. So that's how long that takes. Okay, so I guess what we can do is just make a vector. Make two vectors. I guess we'll do it like this. Vec A is vector dot 0, 1, 2. B, C, D. And we'll say like all right. So the general idea that I have here is essentially what we want to do. Actually, we can still use test max. What we want to do is basically do math on these vectors because we're just trying to test the math, right? We're not trying to test how much time it takes to allocate the vectors. We're just trying to see how long does it take to like index these vectors, do the math, and then move on. So we'll say result. Okay, so vector dot in result dot add oh, we can't do it like that, huh? Result. Okay, so we'll say result 0 equals. I would like this to be a little cleaner than what I'd like. Or this isn't going to be clean because we can't really easily store the output. I guess we'll just do it like this. We can say vector.in vec a.add. See, now we're overwriting vec a. We don't want to do that. Hopefully having the memory tightly packed results in much faster access times. I think it should. Thinking about it now, it definitely should. Vector A. Yeah, I don't want to just do it manually, but I guess I genuinely can't think of any other way to do this. Also, hold on. Getting a phone call. All right, here we go. I'm back. Okay, let me switch the music out real quick. It's classic. Beautiful. All right, Elias, let me see. Jailer says, I feel like having non-slice vectors makes it easier to write code. You don't have to worry about in-memory changes. It's very cheap to create as many vectors as you like because it's all in stack. Maybe so. We'll see. Well, what do you mean by it being on stack? Because it still has to allocate the array. Doesn't it go to heap anyway? Like, doesn't it go to heap if it escapes the function? So if you return an array, if you return something that has the pointer, like an array, doesn't that go to heap? Or am I mistaken? Let me see. Okay, so all right. So here's what we're gonna do. Plus E. I wish this was easier, but we still have to do it for now. I don't think so if it's a fixed size array. Really? Okay, let's check this out. Alright, so let's try this out. Vector math took, surprisingly, not very much time. Am I sure on that? That seems so small. Talking about fixed size arrays. All dynamically sized arrays are created on heap. It is not possible to have a dynamic sized array on stack. Fixed size arrays are on the stack. Okay. Interesting. Oh, whoops, I should be doing b.in. My bad. There we go. Okay, so a little faster to allocate arrays than vectors. Let's try it again. Let's see if we can just run this one. Allocate vectors. Okay, 40 nanoseconds per op. $79 nanoseconds per op. Place on stack if they don't escape. If you allocate a fixed size array in a struct, then check how far away individual elements are in the array. It is a function of how big this fixed size array is. Why is this so slow in comparison to allocating vectors? $170 nanoseconds per op. 39. 46. I wonder if the append function is working as I imagine it should. Capacity 10. Like, this should be correct, but it's definitely taking longer than I feel like it should. This seems more consistent. 33 nanoseconds per op, 42 nanoseconds per op, 114, 38, 50. Okay, let's see. Does this make a difference? .99 nanoseconds per op. Why is it so slow? 117 nanoseconds per op. Let's see. Let's try stopping it before we do this. Way too large, you probably won't make slices that big. It's difficult to talk about performance in YouTube live chat. Maybe so, you think so? Try doing it via in allocations of smaller slices. That makes more sense. Let's say something like this. Yeah, you might be right. Hold on. Let me try this again. One allocation per op. That's right. Yeah, it's allocating one vector per op. Yep, and less dynamic allocations per vector map. Lucretia says, "Is he optimizing for space locality right now?" Like, it makes it sound like I'm like super deep in like some sort of like science, where it's like, is he like trying to cross a black hole using Go and Tetra3D? Is he trying to teleport himself to bring himself back to 1976? It's like, all right. So this seems better. 48 nanoseconds per op, 48 nanoseconds per op, 45 nanoseconds per op. Okay, so it's more reliable. That's better. Okay, so let's try this again. But this time we don't want this. We want this. We don't. And we'll try another one. I just want to see how float 32 stacks up. I guess actually there wouldn't be any difference here because, yeah, there's probably not going to be any difference. There's no reason to do that. Presumably, this is because slices store a pointer. Wait, hold on. Allocate vectors, 50 nanoseconds per op. Allocate arrays, 0.3553 nanoseconds per op. That's more so what we were looking 64, and 0 allocations per operation. Okay. That's what we're expecting. Yeah, that's beautiful. That's beautiful. That's what we want. Lightning. Okay, excellent. So now let's check out if we can do the... Okay, so vector math is 8. There's no allocations, but it's 8 nanoseconds per op. No allocations here. That's correct. There should be no allocations. Okay. So now we'll do the same thing, but we'll benchmark. Alright, so now we're going to say this are... Now here, there might be a difference where float 64 could differ from float 32 because, like, I didn't think there would be much of a difference in allocating the arrays, but in accessing the arrays, it could be a difference. If we have a large number of vectors and we can't fit them all in the cache, then there might be a difference between float 64, vectors, float 64s, and float 32s. You probably get more representative results if you do stuff like vex I equals a.add b for vector.vector. Well, the thing that I don't want to do is do a.add b because, or is do vector.add vector because that creates an allocation. I try not to do that in Tetra3D, so I don't want to like make an example that is intentionally unusual or not representative of the kind of code that I have in Tetra. Like, if I don't usually allocate vectors, if I perform math in place if possible, then I should try to perform math in place like I'm doing here, so I can see if it's just on a fundamental level if it will be faster. So I think this should be good. Let's go ahead and try it. Let's see. All right, allocate vector, allocate arrays, vector math, array math. Okay, so it is faster, not by a huge amount, but it is faster. Yeah. It's pretty consistently faster, not hugely, but by a nanosecond. That's like, an eighth of an improvement. In fact, A, B, and C are probably going to be in the cache. Yeah, probably. Not probably, but definitely will. Maybe even in a CPU register at that point. Yeah, I'd imagine that the cache would have to, like, I would have to make a lot more vectors to test cache. But I can't really... Alright, here's what we're going to do, because I can't really do this the way I would have liked. We're going to say for I is 0, I is less than... We'll say an average mesh, we'll say is... For a PS1 game, let's say an average mesh is comprised of 400 vertices, right? Let's say an average mesh is 400 triangles, which means 1200 vertices, just for an example. B.stop timer B.start. Okay, so we're not gonna we don't want to time the creation of the vectors, so that's this. For this, it doesn't really matter if the vectors, if we're growing the slice or not, or if we make it initially large. I guess we can just do it like this. Make vector.vector upsize. So okay. We can fill it up with random values. All right. So now we do this, and we say vector.in vex I dot add vex I plus 1 dot 1. I don't have any other, say that cross. Something like that. Let's see. This might be better because this should go out of the CPU cache, so we should see a bigger difference. All right, we want to report allocations. We want to. I think this is pretty good. Start timer. So this is point. All right, let's run this. See how this goes. Oh, oops. That's why I was thinking I messed up on something. All right, so very small operate. Oh, whoops. B dot in. Then this should be there we go. Okay, 6,800 nanoseconds per operation. All right, so this, man, that's slow, dude. 6,800 and nanoseconds. Oh, well, calculating the cross product, that's gonna be slow, and that also creates a new vector, doesn't it? Yeah, it creates a new vector. Okay. Well, all right. I don't want to do something that I know I wouldn't normally do. So what we're gonna do instead, because we're testing mostly just the speed of accessing the vector components to do the math on them, as well as cache misses, stuff like that. So, and I don't want to test allocations because I'm trying to avoid that even currently. So what we're going to do instead, we're going to say vex I equals vex vector cross unsafe. So cross unsafe, vex I, that's where it goes. Let's say vex I, vex I plus 1. Okay, let's try that. Let's see what this gives us. Now there shouldn't be any allocations. Yeah, 0 allocations. 10,000 nanoseconds per op. That's crazy. So it's actually slower to do this than the way it worked before. Didn't it create an allocation? Isn't this what this did? No, there's no allocations. How is there no allocations? Because I'm not assigning anything to it, I guess. All right, well, there's no allocations. All right, if there's no allocations, well, this is how I would do something like adding a vector and then doing a cross product. So let's go with this concept, because this isn't like super unusual. This is something that I might do. All right, so 11,000 nanoseconds per op is pretty much what we're looking at, in that range, in that ballpark of like 10,000 or so. All right, cool. So now let's try the equivalent for arrays. Lucretia says, what would create the allocations? Here, when we, like, if we do just like vector, let's say we had two vectors, right? So you have A and then B. These are two. This is an allocation for each of these. This is 2. But if we say a.add b, that creates a new vector that we could store in C like that. So this is a new allocation when we do a function on the original vector. So in this case, add would create a new vector unless we do vector.in. So basically, vector.in means it's gonna perform the calculation and then put the result in the original vector rather than creating a new vector to store the result. All right, so here we're gonna do something like this instead. Float 64, so this is gonna be 64. This is gonna be 64. We're stopping the timer, starting the timer. Okay. All right, so now we would just say vex I 0 plus equal vex I plus 1 0. 2. 2. I don't have an easy way to do this, so we're gonna make a benchmark. I guess we can just make a height that we say like B3D. About 1, 2, or I guess it would just be a B3D. Okay, so B3D 0 is... Alright, well this is what we're gonna do. Not sure if I can do it just like this or... Alright, so now we say cross vex I, or I guess rather, vex I dot cross vex I plus 1. Does this work? No, because do we have to do that? Why did it say? Oh, right. We need this to be a B64. All right. Okay, let's see. I'm not too sure how Go works, but I assume that it would work like Java and stack allocated objects that don't escape the function. Yeah, that's correct. Also, same for C#, where struct is stack allocated and has copy semantic compared to class object. Okay. All right, so this might get us where we're looking to go. Let's see. Let's see. Okay, so allocating vectors, 50 compared to that is 0.3 for allocating arrays. Oh, the array math is slower. Now this might be because we are cross. Maybe this is the problem, because this is the same thing, right? We're adding it. There's no allocations, right? So we're adding vec I plus 1 to vec I. Adding vec I plus 1 to vec I, and we're doing a cross product and storing the result in the original vector. That's what we're doing here. But the thing about this is maybe it has to copy the value. Maybe it doesn't like that. So let's try copying the same function, basically same function kind of information. So B3D and other. So now we can just say cross. Does that make a difference? Oh, no, it doesn't. I was like, it does. It does not. I wonder why. How could this be slower? Code is the same. "20 nanoseconds. Arrays are copied into function. Need to pass a pointer." Oh, okay. So like this. Or 200 nanoseconds per op. Is that faster? I've forgotten. It is. Okay, so it's drastically faster. Okay. All right, that's pretty good. So then could we do it like this? And then just make it so that this is a pointer. But then this would have to be a pointer too. So can we just make it so that this is a pointer to an array? Isn't that what a slice is already? Invalid receiver type B3D64. Am I tripping? Pass by reference. Star B3D. Parameter wouldn't need to be passed by reference. Oh, okay, so just the original? like that. Oh, whoops. Let's see. It's interesting. So it's faster, but it's not as fast as before. 8,000. Other. I think it's 1 or 2. $4,000. Okay, so it is faster if we refer to them as pointers. So can we do it this way instead? Struct data. It's unfortunate this is ugly, but I mean there's not really. Would this work? Is this better? Oops. Oh my gosh. I guess I'm gonna say that's add that's or add let's see. It is for what's let's see how this goes. Or is there an issue? Oops. Let's see how this does. 7,700 nanoseconds per op. So it doesn't like to dereference the data. That's what, well, yeah, that's what the vector is doing basically. Let's see. You already have 2 functions for your vector library. Essentially, yeah. The parameter was copied down to the stack for the function call. So we don't want to have to do this. We don't want to have to dereference it. So it was better when we had it be, when it was like this. But then you have to pass pointers all the time. That's no fun. I'm not sure if there's a solution to that though. If this is faster, this is just faster. Yeah, 4200. Please don't return a pointer in NuVec. Would be better to return a value in that case. Otherwise, Go might do heap allocations. Oh, yeah, you're right. So you mean that we should just do it like this, and then make pointers there? $4,100. Okay, 4,100 nanoseconds per op. That's good. That's fast. But that's not really good looking though. Can we? Well, we're not. Well, we don't want to have to copy, so we have to make a pointer. Losing locality otherwise. You're a madman for optimizing on stream. I feel like a madman. Let me see something. Hold on. Let's see. Okay. Well, I mean, for today. I'm trying. I don't know what to do. I mean, like, this is definitely faster. So this is how it should work. But like, it's ugly though. Like that's like if we're gonna be replacing vector.vector, then it needs to be comfortable for other people too. It can't just be purely for Tetra3D. Yo, this was dope. I like just the jazziness of this. This is kind of dope. All right, anyway. All right. Okay. Yeah, it's kind of ugly. Can we not have to do this? Can we not have to do that? In order to not do that, we have to basically make it so that new v3D returns a pointer. It has to return a pointer. I wouldn't want to use vector.vector outside of Tetra3D though. I always needed to convert my own vectors to vector.vector. Can you do some weird type stuff to hide the pointer part? Twice as fast. It's yeah, it's a lot faster. It's 3 times faster because this is 1200 nanoseconds per op. 10,000 nanoseconds per op. So to go from 10,000, I think, up to 11,000. To go from that down to 4,000 is almost 3 times faster. This is this is non-negotiable. Like we need to implement this. This is a drastic improvement. It's just about how can we do it. Actually, let's also test float 32s as well. I just want to see real quick, would it have made a difference or does it make a difference? I guess we can just do it like this. I guess I could have just, now that I think about it, let me go back. Okay, so this is what we had, right? This was working. Alright, so we're sitting at 4,100 nanoseconds per op. Let's just change this to be float 32s instead. To see if it changes at all. It was like 4,000 nanoseconds per op. 3,800, 70. 4,209. 3,900, yeah, 20. So it's not a huge difference between float 64s and float 32s. So it seems like the lion's share of the optimization comes from maybe not having to dereference pointers that much. 4,600 with float 64s, 4,600, 4,300. So it kicks it down by like 300 nanoseconds. Oh no, that's 4,000. 4,300. So it's not a huge savings to go to float 32s. If I with pointers, that might work. 4,400, 3,900. So yeah, it's not a huge difference. It's float 32, float 32. Let's try something real quick. I just want to see if this makes any difference at all. Let's say we were doing with 12,000 vertices. Okay, 43,902 nanoseconds per operation. Now let's switch over to float 32s instead. Oh. Does this make a difference? 40,000 nanoseconds. 38,000 nanoseconds. 40,000 nanoseconds. 41,000. 45,000. 46,000. Alright, so I mean, like, I guess we might as well do it in float 32s, as it is faster, if it only by a little. Going from like 42,000 average to like 39,000 average, 38. So that, you know, that's not a huge difference, but that's something. So it would make sense to be float 32s instead. So that means Matrix 4 is also going to need to be float 32. So that's fine. It's just the API now is just not, I don't want to have to do this. Do it like this. People writing new X star type by default makes me sad. A lot of structs can always be on stack, but this prevents it a lot of the time. The fun thing is that going from pointer to dump struct and value semantics almost always gave us huge performance improvements. I wouldn't want to use vector.vector outside of Tetra3D. I thought vector.vector was a fine vector, well, is a fine vector class. Like, it works fine. It, you know, it's, I mean, I guess I would prefer to have like just a firm 3D vector or 4D vector. And 2D vector. Like, you know, for 3D you need both 3D and 4D vectors, and you also need 2D vectors for like UV values. Well, you don't need them for UV values for Tetra3D, but like you could definitely use it for 2D games. So like having 2 through 4D vectors is useful. And you know, the approach of vector.vector is very clean in that it's one struct that you can make to, you know, be any dimension that you need. But it seems like it'll be faster if we can do it like this. So does this mean that if we, like, is new function returning a pointer to a type, to a struct, the same as running new function on putting the result in a variable, then getting a pointer to that variable? Because I'm thinking, like, how are we going to store this data? Like, we're going to put it in here. It's going to be v3ds here, and not pointers, but just raw v3ds. Maybe that would be better. It'd be crazy if at the end of this we end up with like a 3 or 4 times speeding improvement. That'd be insane. In 3D, you'll need 4D vectors 90% of the time, though, just like you need 4x4 matrix classes. Well, yeah, I mean, but also 3D vectors. A slice of pointers to dumb structs. Yeah, I suspect the speed up is going to be pretty good once models are involved. It might be a pretty large improvement. You could just have a vector 4 struct and methods that make it act like a vector 3. That's true. You could just have a 4-dimensional vector and then just like not just leave the 4th value as 1, really. That covers most of vector 4 usage anyway. And just be like, ignore the 4th value. Oh, we don't like this, right? We don't like it where, why did I do data? We don't do this with data. Yeah, this was how it's supposed to be. So, whatever. Anyway. Alright, so something like this. I guess really would be. So it would just be a 4-dimensional vector. Well, yeah, I guess that makes sense. Or it's just a vector. It's just a 4-dimensional vector because that covers RGBA as well. UV, and then we can just ignore the last 2 values. Even in 2D, you could use it by setting Z to 0. So maybe just a 4D vector and ignore the last 2 values for UV or for, well, if I use it for UV, I don't think I do. Okay. Rotating would not work for a 4D vector, or it would just ignore the last point, the last value. So something like this. So it's just, so this is just V, we could just call it a vector. Okay, so we got add, we got cross, we'll need sub. We don't need sub. I guess, yeah, it can't hurt to have sub. We'll need rotate. We'll need normalize. We'll need length. So this is going to be a 40. Oops, back. That, okay. Get X is cleaner. No need for get X accessing by X, Y, Z is better than W. Then, well, it's better to just say W is undefined if we don't use it. I get X is cleaner. Yeah. Well, the thing, the Go, like, I think the Go, can't think of the word. Like the style guide is like you don't use get, you just use the word. Like you have variable and set variable functions. You don't have a get variable function. It's, that's fine. Either way is fine. But if you X, Y, Z, V, okay. Yeah, I'm not sure if I would even have a X, Y, Z function. Maybe, I don't know. How would I do swizzling? That would return a new vector. Well, yeah, I guess that's pretty simple actually. You just say like func back swizzle, and then you say like indices dot int. You could just say, yeah, it would have to be it's less than 4. Something like that. I guess you could say okay, that's the idea. The swizzling is there. I mostly think there's different to get X cleaner, by the way, beginner friendly. Oh yeah, the reason why I want to have a vector class or a vector type that is usable with beyond Tetra3D, outside of Tetra3D, like for the user who's making a game, is because it's awkward to like always have to convert types like you're doing. Elias, like you're converting between the vector type and your own vector type, and it's like you can do that, of course, but it's like, if we can have a vector class that's usable and performant, that would be good. Cross product, that should work. Yeah. Length, normalize will also have to be done. It'd be good to have a length squared function as well. This might be dumb, be careful with cross. Wouldn't be the first expression effect. Wouldn't it be that the first expression affects the second and so on? No. Oh, wait. Yeah, you're right. Okay. Thank you for catching that. You're super right. Thank you. You're super right. That would have bit me in the booty. Hardcore. I would have been like, what? No way. All right, 0 vec. This could be 1. I mean, I guess we could make it so, well, we need it to be 4-dimensional because there's 4-dimensional vectors. We do 4-dimensional math or math with 4D vectors. That's pretty important. We can't just ignore 4D maths. Float 3 or float 4 func to convert it easily to an array of 3 to 4 floats. That makes sense. Well, I guess this would just be... just like, I mean, I think you might be able to, let's see, can't convert, oh, that's to, there we go. Or, we'll just say floats. Let's see, this will cost, add sub, new vec, zero vec. I don't like this. Maybe new vec 0. New vec 0? What, maybe not unit. What's a vector that's like it's 0 thing? Let's see. You can just do it like this. Yeah, that's what I am doing. Casting the floats. Yeah, we're good on that. I guess we could do like a 3D vec instead of 4D vec. Well, that would throw off the length, wouldn't it? Now that I think about it, this has to be 0. Oh no, how do we do this? What do we do? I guess we just don't calculate the fourth value when it comes to length. Oh, that feels wrong, dude. That feels super wrong. What if, yeah, it feels wrong to have the fourth value be there and have length and length squared and normalized just not touch them at all. That feels weird. Elias says, I start with float 64 first for vec. It's a little annoying to convert from float 64 and back to float 32 over and over. It would make porting from vector to vector faster as it uses float 64. Well, I mean, it doesn't make sense to use float 64 if float 32 is definitively faster, right? Like, we know that it's faster. We know that it's some amount faster. It's like, I don't know if we have the data, but wasn't it like 10% faster? 5%? Like, if we're gonna remake it from scratch, why would we go with the slower version? Your matrix class is 4.4 float 64 though. Yeah, I was gonna change that to float 32s. Why would I go with slower? Why would I go with something that I know is slow? And I mean, like, the matrix class is like very little of it is using float specifically. Like, once we switch it over to float 32, we could probably do it, just find and replace. That should be simple. 1,000 units faster, 3,180 versus 4,280. So it's almost a quarter faster. Well, no, it wasn't 3,180 all the time. It varied. It wasn't like, the average wasn't 3,000. The average was like 3,900, 3,800. So I would have to switch matrices. I would have to switch. Response, okay. Would type vec3 struct vect and type 4 struct vec work? Then you could specialize length on vec3 and not on vec4. Yeah, I'm wondering if maybe I could do like a vector is just. Oh, hold on. Okay. I'm wondering if I could do like a vector is just a array of 4 or 3 floats, and a vec3 is something that acts on a vec, or vec4 is something that acts on a vec. Maybe it wraps a vector. So that would allow us to make some code that has, like, it embeds a vector. So the base vector code has swizzle, it has, well, it wouldn't be able to have add. No, it can have add, it can have sub, but only vector 3s have length and normalize. And cross. That's an idea. It's an idea. Length on Vec 3 and Vec 4. Yeah, that's what you're saying. Okay, yeah. So that's what you're saying, Baxter. Like, embed it. Yeah, I think that's on the right... I think that's on the right track. I think we can make it so that a Vec... You can't actually make a Vec. We can only make 3D or 4D Vecs. Which embed Vec. Or I guess it's just an alias. That. Like that. And then we can make a differentiation, but share almost all of the other code. Because when you add vectors, it can add, yeah, because then a new 0 vec could be this. But I just have to remember to set the fourth value to 1. Well, when you make a new vec 4D, that could be the value for vec. Okay, so new vec 4D 0, and it's vec 4. I guess we could just say 4 vec 4. Vec 3. Okay, so then, okay, so now we can say this should still work. Any other vector. Does this make sense? Like, I'm wondering, like, will this work? Like, if we say TV equals new vec 3, and then like TV dot. Yeah. So why don't we have add here? Vec add. Oh no, that's no good. So it would have to, I think it would have to embed the struct to get access to its functions. You need type vec3 equals vec. That's what this is. Right? Am I, no, type vec3 vec is different. Really? Really? Okay, hold on. Let me look it up. Golang type alias. Let's see. Type an alias declaration has the form type T1 equals T2, as opposed to a standard definition type T1 T2. The alias declaration doesn't create a new distinct type different from the type it's created from. It just introduces an alias name T1 and alternate spelling for the type denoted by T2. Really? Are not meant for everyday use. They were introduced to support gradual code repair. Where's the emoji? Let me see. Hold on. Let me see if I can find it. Hold on. Where's the emoji? There it is. this emoji. Like they're like, it wasn't meant for everyday use. I'm like let's see. But you won't be able to make different functions for vec 3 and vec 4. Oh, I won't be able to. Oh, I see, because it's an alias. Okay, well, yeah, but there's not really much of a point. Struct embedding, but the thing about struct embedding, I'm not certain that if I embed the struct, gotta keep this open, make sure. I'm not certain if I embed a struct, if you can embed like it's not a struct, right? This is a type. This is a declaration. like I can't just like I could do struct, but that would mean that does this work like this? I don't know if this works like this. Let's see. 2 back 3. Yeah, it doesn't work. Can't use 0 as vec value. So that would have to be a vector like this. So then it would be vec.vec. Let me see, hold on. Yeah, see, that doesn't work. Yes, that's not good. That doesn't quite work the way that we would like it to. Because I think we want to avoid dereferencing or referencing pointers when doing math with vectors, right? Because it's so... we're doing so much of it in a single, you know, instance, in a single frame. So it needs to be like almost instantaneous. So we can't put stuff in a struct because that means that we have to get to it. Better to copy paste some code. Embedding is not good for initializing API usability. The alternative. The alternative is just to have it like this, where a vector is 4-dimensional. But there's no such thing as a length for a 4-dimensional vector, right? Like no one would. Let's just work with the idea that a vector is fundamentally 4-dimensional. Because really, the only time you need the last value of W is if you're combining the vector with matrices. Otherwise, it doesn't matter. You don't think about it. You don't know that it's even there. So maybe that's fine. Length of 4D vector is length of 3D vector, yeah. I mean, it's just really, you know, I know mathematically a 4D vector means that it has a length, you know, the fourth dimension of W contributes to the length, but in game development, I think it's fine for it to just be like, it doesn't matter, you don't think about it. Now length, I'm just going to create some of this code from vector.go. Let's see. Unit and magnitude. Oops. Okay, so if it's 3-dimensional, then we return the square root of a x plus y plus z. Okay. Oh, it needs to be a float CC4. Okay, we'll contribute. Squared means that we can just avoid using the square root function. Should it be float 32? Does that make sense? I guess we'll make it consistent with that. Normalize is unit, and that's over here. Is situation is 3. Okay. So square root, and then if L is less than this, return A. Oh, I see. So it don't touch it essentially. So this will just return. So this is the length. So we could probably just use length squared, right? Like if it's not the square root, if we don't get the square root, we can just assume, like we could just do like this, right? Like vec dot length squared, and then if it's less than this times this. Or maybe just like something like that. I'm so bad. Okay. All right, so we have normalized, we have length squared, we have add, subtract, we have swizzling, we have swizzling. One less than 3 values, 4 values. We'll say it's less than 3. And then, yes, this could have 1 as the last one. That's fine. Okay. Cross product. Cross works. Let's see. All right, so this should kind of work. Vector represents a 3-dimensional vector in space. 4-dimensional, a vector in space. It has 3D vector functions. So something like that. Subtract length. We need to rotate and angle. Let me actually. What's the license on Mr. Vartborg's? Mr. K. Vartborg's. What's going on? Firefox was kind of tripping. Let's see. Oh, Quarter Castle now. He changed his name. What's the... Is it MIT? It's MIT. What's the MIT license? Okay, I think it's... That should be okay. Should be fine. Should be fine. Should be fine. Okay. All right. Well, I'm not sure. I think my time has run out. But this is pretty good. We managed to get to basically understand the general idea of what we should be doing here to make this run faster. It's exciting that allocating data should be faster. It's exciting that doing math should be, significantly faster, going from what was it, like 11,000 nanoseconds, 12,000, 10,000 nanoseconds per operation to 6,000. Wasn't it 4,000 before? Wasn't it 4,000? But was I? It was 4,000 before. What did I do? What happened? Why is it 6,000 now? It's weird. I'm not sure. Nothing. I feel like I didn't do anything that changed this that much. Start timer. Cross. Well, in any case, cross wasn't right before you changed it. Oh, that's right. Oh, yeah. That's right. It was incorrect. Thanks for that as well. I'm gonna go back and say that again. Thank you for that, because I would have been like, what? Thanks, Maxter. I'm not sure if there's a way to do this without creating a new variable. I guess we could create a stand-in variable like this. I'm not sure if this makes any kind of a difference, but let's see. I'm not sure if this works at all, but let's take a look. Because this would allow us to avoid creating the variable, so maybe that will make a difference on this order of magnitude, but nah. Yeah, I'm not sure what's the difference then. We don't have any allocations. Maybe it's just slower because we have to store the result. That's just what it is. It is what it is. Okay. Yeah, like what happens if we just... I mean, I know what will happen, but I just want to confirm it. Like if we just say cross doesn't do anything. Yeah, it's faster. Okay. So it is about just what's going on in here. I hope you don't get to the level, need to get to the level where you have to count floats that you create on the stack. I hope so. I hope I don't get there. I just want to just be able, I just want to be able to kind of take a look at my code and be like, this seems like it's slow, let me optimize that, rather than being like, you know, let me take a look at the assembly output and let me like, you know, what's this address it keeps referring to. I mean, like, you know, at a certain point it's like, I got things to do. I can't be spending time like this. But yeah, okay, so this is pretty good. We got most of a vector class written. We just need angle, rotation. That's kind of it. Because we already have code to multiply a matrix by a vector. It's just in our matrix code. So we'll just adapt that for our new vector class. I'll have to kind of review this all because this is basically operating under the idea that, you know, we're multiplying a vector and you know, like we're well, it would have to be, it would be P. Oh, I see. Right. So yeah, I'll have to figure out, I've got to figure out how I'm going to do this, because some of these times we're going to need to create vectors, and some of these times we're going to operate into vectors, like multiplying a vector. That kind of makes sense to put in the vector. So like, you know, we return, well, the original vector is modified by the multiplication process, but I didn't write this so that it worked that way. So I'll have to double check. All right, but this is a good start. This is a good start. I'll need to go, I believe, because I think my time is up, maybe. But anyway, thank you very much for watching. It's been real, it's been fun. You can do cross without the temporaries in this order: vec2, vec1, vec0. Oh, hold on. I didn't pay attention. You might be right. Let's see. So you're saying this first, so vec1, vec0 and vec1, and then vec2 and vec0, and then vec1 and vec2. Yo, you're right. Dang, that's crazy. I completely just didn't even pay attention to that. Now we're down to 4,000. You're crazy. You're cracked, Maxter. You're absolutely cracked. You're cracked, dude. This is insane. That's insane. You brought it down. You literally saved like half. No, you're right. You're right. That's correct. Because when vec2 is being written, you're reading vec0 and vec1. When vec1 is being written, you're reading vec2 and vec0. Oh yeah, the original vec2 is lost. Okay, never mind. But you're still cracked. You're still cracked. That's sick. Thank you for the suggestion. Elias says, thanks for the stream. I hope I didn't get you too sidetracked, but I believe it will bring more profits than simply switching from float 64 to this float 32. Yeah, I think you're right. I think that fundamentally the cost of dereferencing pointers is high enough especially when you're, well, it's probably it's minimal when you're talking about like making pointers to game objects in your game, where it's like I have 28 game objects, 20 or 30 game objects in my game, and I have to like update them all. It's like, well, the cost of dereferencing those pointers is on the order of 0.1 nanoseconds. It's nothing. But when you're talking about dereferencing 20,000 vertices, or 5,000 vertices across 30 or 40 game objects, 30 or 40 models, and their meshes, that adds up. That dereferencing is adding up. So yeah, with the array versus vector changes, Tetra3D will be so fast. Hopefully so. Hopefully we'll see a massive improvement where not only is it running faster, but it also loads almost instantaneously. Tetra3D already loads really quickly. It loads very fast. But that's mostly because it's a low poly. It's made for low poly games. So you're loading 1,000 triangles, maybe a few hundred triangles. It's not a big deal. But with this, allocating vectors, or allocating our new vectors, should be faster, and then performing the math should be at least twice as fast, which is great. I feel like actually let's go back, because we could do this. We just need to store the original vec2. We just need to store the original vec2, so that you read vec2 is vec0 and vec1. Vec1 is the OG vec2, and vec0, which hasn't been written, and then vec0 is the OG vec1 and the OG vec2. Okay. All right, well, this still could be faster. OG vec1, OG vec2. There we go. Let's see if this is faster. This might be it might be a little faster. Yo, 4,000 nanoseconds. Let's go. Okay, so we might have just slid in like just under cache or something. Like that, well, I don't think that's what it was, but let's just go back and rerun these tests. I want to see 6,000. 6,000. Okay, so yeah, this definitely is faster. 3,000, 3,700, 3,400. 3,500. Fantastic. So OG vec1 is vec1, vec2. Okay, so now vec2 is vec0 times other 1, other 0 times vec1. 0 and 1 haven't been altered. Okay, 1 is using the OG vec2. 0 hasn't been altered, so we can do that. And then it's using the OG vec1 and vec2. Okay, fantastic. You're cracked again, Maxter, because your suggestion was fantastic, even though it wasn't immediately correct. The idea was fantastic. Yeah, so we don't have to store stuff. Okay, excellent. Elias says ray tracing and Tetra3D win. Who knows? Who knows? But this is good. This is shaping up. So we just need to finish the vector code and then make it more good. But anyway, thank you very much for watching. I've been SolarLune, and we'll see what happens next stream, what this looks like. It might be that I managed to get everything squared away, and you'll be looking at a faster Tetra3D. Who knows? So anyway, thank you for watching. I've been SolarLune. It's been real. If you want to support development, please check out the links in the description to Master Plan and my Patreon and things like that. And I'll catch you on the flip side later. See ya.